Okay, on to our next speaker, Dr. Jared Lloyd. Jared is a postdoctoral researcher within the Australian Critical Minerals Research Centre at the University of Adelaide and also an adjunct researcher with Geological Survey of South Australia. His background is in the Neoproterozoic geology of South Australia. However, his current research has pivoted toward rare metal LCT pegmatites, which he will be presenting on today. Welcome, Jared.
All right, so my talk today will be sort of taking about half of it will be on pegmatite formation and kind of the prospectivity of South Australia from a geodynamic perspective. And then the second half of the talk, I'll be looking into some of the advances we're making around geochronology at the University of Adelaide, particularly with the support of the survey here, to allow us to date things that are either directly or mineralisation, but also to give us more robust and accurate ages of various events that happen, unravelling geologic history from some things that aren't a bit more traditional, like zircon. So I'd just like to add my acknowledgement to the Kaurna people and pay respect to their elders past and present. So globally, there's quite a few lithium deposits around. There's broadly 3-4 classes. So you have the brines, which you can see in South America there, all the nice big blue circles. There's these volcanosedimentary and sort of clay deposits, which they're sometimes split into different deposit types, but for the most part they seem to be formed from the same initial circumstances with slightly different upgrading going forward with them. And then you have the big pegmatite deposits. So WA is definitely known for this, supplying about half the world's lithium at the moment. You'll see there's a fairly big gap when it comes to Eastern Australia and certainly in South Australia. Arguably there should be at least one pegmatite deposit popped on there. Whether it becomes economic or not is a whole other question. So when we're looking at brines, some of the key features, so you require the presence of a closed or semi-closed lacustrine system in an uplifted highland area. So this is why, particularly in South America, you're talking elevations well above 1,000 metres, really high evaporation rates. The other things that they need to have fairly active hydrological systems below them, connections to geothermal systems to increase the lithium component coming in. So this may be a magmatic source nearby or further leaching of felsic magmatic systems and their deposits afterwards. And it needs to be in a fairly readily leachable form. So this is something like volcanic glass, so thinking of rhyolitic type magmas. So in South Australia, so Geoscience Australia did a bit of work a while ago, and there were a couple of companies who were looking at this. So SA salt lakes have some of these key features, but their main hindrances are the fact that they're fairly flat topography around them. So they are a central drainage system, but it's not pulling in from really high areas. They're somewhat intermittently closed, so even Lake Eyre has only been a closed system for about 42,000 years, whereas most of the Argentinian ones you're talking upwards of about 100,000 years or so. And their distance and connectivity to geothermal systems. So while there are hot springs on the nearby margins, they're still a little bit more distant than what you would see from the Argentinian and Chilean deposits. So it is likely that they have some potential, but it's probably pretty low in terms of economic extraction. In terms of lithium clays, so their source is still debated, thought to be sort of two origins. So volcanic precursors of a clay enriched in lithium or supergene and hydrothermal alteration. Realistically, it seems like it kind of need both to happen, and it then changes the grade of the deposit itself. So the biggest one, Thacker Pass, effectively started off as a caldera. You have the rhyolitic magmarina, and then there's a hydrothermal alteration that's upgraded that significantly since. They occur in these closed lacustrine basins with high evaporation rates and really high salinity. So the alkalinity of these systems is really important to actually form and hold the lithium there. When we're going on to pegmatites, so these are kind of the ones that are a bit more interested in Australia, so particularly WA and Northern Territory have known potential for this. Victoria, there was one found recently as well, and there's a couple in New South Wales. There are two models when it comes to pegmatite genesis, so either a residual melt of granites or the direct product of anatexis. I'll have a slide a bit later on that has a diagram that kind of shows this. They crystallise in a matter of days to years, so they're really super quick compared to most other systems that we think about. And one of the really key things about most of the pegmatites around the world is that they're emplaced into orogenic hinterlands. So this is where you have an abundance of metasedimentary rocks and igneous rocks coming forth. The other thing is that they do appear to be related to supercontinent cycles. which is what this next figure is showing. So we've got a map of the pegmatite occurrences around the world, coloured by their age. And then on the bottom little graph there with the histogram is showing the count of the pegmatites in that bin by about 20 million years, and the little lines showing the cumulative surface age distribution. So pretty consistently through this, we're finding that they're tying up with either the starts or ends of supercontinent cycles, which are what those grey bars are representing. So, in terms of the petrogenesis and this model that I was talking about, so on the top we've got, when we're looking at magmatic-based petrogenesis of pegmatites, and on the bottom half is looking at the direct product of anatexis. So, within the magmatic systems, effectively thought that you have continued fractionation until you get to a highly enriched state where you have elements such as fluorine, a lot of fluxing things like water, lithium and beryllium, cesium, rubidium. So a lot of exploration techniques use these as proxies, and it's a pretty good way to look for them. Unfortunately, the footprints of them tend to be basically sitting on top of the deposit, so you have to be pretty lucky to kind of run over it. The other thing that is to note about these sort of elements is they tend to be quite mobile. So lithium is one of these where there's actually a lot of lithium around. It's really easy to find lithium. It's really hard to find lithium in a very high concentration though, because it's very mobile. And the other graph that's on the left-hand side there, what this is really just trying to highlight is that one of the key features of really enriched and economic pegmatites is that they have undergone what we call undercooling, and a really high amount of that. So that's effectively pulling the crystallization temperature of the pegmatite well below what is the liquidus solids boundary, so that they have to crystallize really rapidly. What we find is that in the current economic pegmatite systems, they've undergone this undercooling to a really high extent and formed very small but very enriched deposits. You can get very large but very sparse deposits forming if you don't have that undercooling component. So this is a really important thing to understand when you're looking for pegmatites and what the pegmatite is going to give you in terms of mineral components. So in South Australia, there are some really interesting pegmatites in the Yaleri region that are noted as being of LCT class. They have in past been mined for beryl. But some prior research by, I think it was Lotomoser back in the 80s, suggested that they're of the beryl columbite phosphate type rather than the pure lithium end member. It is important to note though that those particular assemblages, so the beryl columbite and phosphate or lithium phosphates, tend to form on the margins of even the bigger pegmatites that have spodumene at their cores. The nearby Broken Hill block contains very similar pegmatites in the same region, so within the Curnamona, and these do have a very high abundance of lithium phosphate, so the montabrasites and ambligonites. So there certainly is lithium around. Whether it's extractable is another question. There's a really big challenge around trying to get lithium out of the phosphates, particularly when you're looking at the montabrasite and amblygonite, because there's usually quite a high percentage of fluorine in them as well. The other place that's really interesting, so Dudley Peninsula, there is a gem quality albaite, and it was traditionally mined for that for a long time. So these are the very bright pink and blue tourmalines, so the alkali tourmalines. They do have a significant amount of lithium in them. There was some soil samples done which ended up showing that the area is also enriched in lithium, rubidium, cesium and tantalum at quite substantial levels. It's very possible that this is just looking at the surface of a lithium pegmatite, and the spodumene core, if it's there, is a little bit deeper. The other things that are really important to think about in pegmatites is when they tend to occur in an area, they tend to occur over multiple generations. So if you find one, you're often likely to find more. They're also one of those where you tend to find other commodities coexisting with them really well. So while lithium's sort of the key one here, it is also that these pegmatites will contain quite significant amounts of rubidium, cesium, tantalum, beryl, so beryllium, and high purity silica if they haven't fractionated enough to get to the lithium stage. Unfortunately, a lot of the pegmatites through the Adelaide Super Basin haven't had a huge amount of work done for them. So I know there's a mention of some stuff around Jacobs Creek, but the mention of that was back in the 1800s. Since then, beyond the work that's being recently done, there hasn't been a huge amount in that area, with the exception of the one on KI. Now, the other thing to consider here is these are likely tied up with Delamerian origins, so they're intimately linked with the Gondwanan supercycle. All right. And then moving on to geochronology. So how do you date pegmatites? Well, Columbite, tantalite, sometimes zircon if you're lucky. Usually the zircon's really high uranium, so it doesn't work very well. Apatite occasionally, but often is secondary. So these are the traditional systems where you're using uranium lead. What we've been doing at Adelaide is developing methods to use beta decay systems. The challenge with beta decay systems is that you're looking at a parent to daughter product that doesn't actually change the mass. So when you're using a mass spectrometer, that is a really big issue because you can't resolve it. So some of the systems there, so the rubidium strontium, traditionally done by solution, lutetium hafnium, rhenium osmium, which has been a big thing in the petroleum world, potassium calcium, which is a very challenging system but could be quite useful, and then lanthanum barium. What's changed? Well, in the last 10 years, we've had this change of machinery. So on the bottom, we have the traditional ICP-MS, so inductively coupled plasma mass spectrometer. Fancy thing, it just measures mass. Above it is the newer version. So all they've done, and you'll see there's an extra cell added in about here. So you've got this quadrupole, cell, quadrupole. What that allows us to do is set a filter for an element coming through, then react it, and then set a filter for an element coming out. With that, we can react off products selectively, so we can take rubidium, run it through, and it'll come out the same mass. We take strontium, run it through, react it with some nitrous oxide, and we'll get a different product, so we can effectively resolve the two and then measure them in situ. What it works really well on is lithium pegmatites. They have a huge amount of rubidium in their micas. So this one is from some California deposits, where there's previous geochronology done on these, and these are thought to be related to a subduction cycle. The previous age that's been determined is around about 100 million years from argon-argon. We've managed to get a weighted mean age from this because it was so radiogenic of 103 million years. The biggest difference between the two methods, though, is the method that we're using here takes a matter of a couple of days. It's a matter of getting the material, setting it into a little puck, and then running it through the laser. The argon-argon takes about a year and a half, depending on which nuclear reactor you can get access to and how fast they can turn it around, and then how long it takes for it to cool down so you don't irradiate yourself. It's also a lot cheaper to do it this way as well. Potassium calcium. So this one could be really useful because it works in the same sort of systems where rubidium strontium will work well. What we're hoping to be able to do is then actually develop Concordia diagrams so we can effectively do the same as uranium lead and then assess the quality of our data on the fly rather than having to go through complicated methods to make sure that our data is reflecting, say, mineralization age versus some alteration later on. Rhenium osmium is another one that's been developed, and this is really useful for molybdenites and if you've got the right kind of pyrites. So you'll note that there is a concentration up here. You need to have those sort of concentrations for it to work. But this is the way that we can directly date an ore formation. So we're not having to use something like zircon as a proxy to try and understand when a deposit's forming. So this is kind of a summary slide of what we're working on. So uranium lead's the traditional thing. These are all the different minerals we can do at Adelaide. I should have actually added, I haven't on there, badleyite as well. Rubidium strontium, we've got a whole bunch of things we can do, and then a couple of things that I'm working on, so cesium beryls and the lithium micas, and they're fairly advanced in their development. We're just trying to tie off a few loose ends. Lutetium hafnium, this has been working particularly for the carbonates, so things like calcite and calcite veins. Rhenium osmium is working fairly well for a lot of minerals for ore. And then lanthanum barium is kind of the final frontier that we may or may never ever get working. It's a really challenging system. If we can, then it'll allow us to get secondary ages off of some of the rare earth rich phases. And thank you for your time.